Let us understand refraction through a prism. Consider a glass prism whose cross-section is shown below. AB and AC represent two refracting surfaces. The angle BAC is the angle of prism and is denoted by capital A. The angle of incidence and reflection at the first phase AB are I and R1. The angle of incidence from glass to air at the second phase AC is R2 and the angle of refraction R1 or emergence is E. The angle between the emergent ray RS and the direction of the incident ray PQ is called the angle of deviation delta. In the quadrilateral AQ and R, two of the angles are right angles at the vertices Q and R. Therefore, the sum of the other angles of the quadrilateral is 180 degree. In quadrilateral AQRN, angle A plus angle Q plus angle R plus angle N equals 360 degree, in which angle Q and angle R are 90 degrees. Therefore, angle A plus angle N equals 180 degree. Comparing these two equations, R1 plus R2 equals A. Now, in triangle MQR, angle I equals angle MQR plus R1, or angle MQR can be written as I minus R1. This implies angle MRQ equals E minus R2. As angle QMR plus delta equals 180 degree, we can write angle QMR as 180 degree minus delta. So, according to the triangle's property, we have angle MQR plus angle MRQ plus angle QMR equals 180 degree. This implies I minus R1 plus E minus R2 plus 180 degree minus delta equals 180 degree, or delta equals I minus R1 plus E minus R2. So, delta equals I plus E minus A. Thus, the angle of deviation depends on the angle of incidence. Given is the plot between the angle of deviation and angle of incidence. This is the plot of angle of deviation delta versus angle of incidence I for a triangular prism. At the minimum deviation, dm, the refracted ray inside the prism becomes parallel to its base. QR is parallel to BC. Also for delta equals dm, I equals E. If I and E are equal, then angles of refraction will also be equal. That is, R1 equals to R2 equals to R. Put this in R1 plus R2 equals to A. This implies R equals A by 2. Also for delta is equal to dm, we have I is equal to E. Hence, the total deviation delta is the sum of the deviations at the two faces. That is, delta equals I minus R1 plus E minus R2. That is, delta equals I plus E minus A. This implies dm equals 2I minus A. This implies I equals A plus dm by 2. If the refractive index of the prism is n to 1 with respect to air, we have n to 1 equals n2 by n1. This implies n2 by n1 equals sin I by sin R by Snell's law. This implies n2 by n1 equals sin of A plus dm by 2 divided by sin of A by 2. The angles A and dm can be measured experimentally, and thus This equation provides a method of determining refractive index of the material of the prism. If R is small and with a very small angle of prism, that is a thin prism, dm is also very small. We can take sine of a plus dm by 2 as a plus dm by 2 and sine of a by 2 as a by 2. Hence, n21 equals a plus dm by a. This implies dm equals n21 minus 1 whole multiplied by a. It implies that thin prisms do not deviate light much.